So let me start with a summary of what we did last week. Last week we introduced the concept of virtual work. So we call that delta W, and the virtual work that's done by a force is defined to be the dot product of that force with a virtual displacement vector delta Ri. So Fi is a force, and delta Ri is a reversible virtual displacement in harmony with the constraints. We'll call it the kinematic constraints. What does it mean for a virtual displacement to be in harmony with the kinematic constraints? It means it's a virtual displacement, so it can be unphysical in that it's not the true displacement that the system would follow as time goes through. So it's virtual in that sense, but it can be, it must be in harmony with the kinematic constraints. It means it can't be unphysical, such as a block going through a wall. So if you have two masses, for example, that are connected by a bar, maybe the two masses are falling down with gravity, so an allowable virtual displacement would be for the two masses to both go upwards, but not apart from each other. If they were to move apart from each other, that would violate the constraint that they're connected by a bar. Okay. So the point of this virtual work was to introduce the principle of virtual work, and the principle of virtual work says that for a system in static equilibrium, by static equilibrium, we mean the same thing that we do in first-year mechanics, when the sum of the forces and the sum of torques are equal to 0. So for a system in static equilibrium, the total virtual work done by all forces is 0. So the sum, let's say we have capital N forces, so the sum of the virtual works for all those forces must equal to 0. And we saw that this was a useful way to handle statics, because what we call internal forces can often be ignored. for example, forces from what we called workless constraints. So we saw, for example, tension, normal force, reaction forces, which are really just normal forces, etc. Those all turn out to be forces that don't do any work. And they typically don't do any work because the only component of F dot delta R is inconsistent with the kinematic constraints. So the normal force, for example, can only do work along the component that's parallel to the normal force. So by definition, a normal force is a force of contact between two surfaces, and it would violate the kinematic constraint to have any displacement that's perpendicular to a surface. That's the principle of virtual work. Now, last week we continued by rephrasing this principle of virtual work using our formalism of analytic mechanics. So of course it already contained delta R in there, but we pushed it further and we expressed it in terms of the generalized coordinates. So we introduced the concept of a generalized force. So we wrote that the sum of all the virtual works, so the sum of the delta Wi's, we wrote that as a sum over the n generalized coordinates. So note the summation is over j up from 1 to lowercase n. And we found that we could write this as sum of qj, capital Qj times delta lowercase qj, where we introduced capital Qj as the sum from I equals 1 to capital N of Fi vector dotted with di Ri vector by di Qj. So Qj, lowercase qj are the generalized coordinates. And so there are lowercase n degrees of freedom. And so this capital Qj is what we call components of the generalized force. And for static equilibrium, so the principle of virtual work, for static equilibrium, the total work is 0, and what we find is that the Qj are equal to 0 for all j. The little symbol there means for all possible values of j. So we have two ways to solve a statics problem. One is to explicitly calculate the virtual work and set it to 0, and the other is to calculate the components of the generalized force and set them equal to 0. Any questions about that? So after that, I gave you a procedure for solving these static problems using this new method, and we did one example, which I believe is example 3.3. So let's do another example today to start off on this principle of virtual work. We'll do example 3-4, and then after that we'll leave the last example for Thursday. We'll do more of a tutorial session on Thursday, and then we'll continue with D'Alembert's principle. Okay, so let's do example 3-4. This is sort of the classic ladder problem. We have a wall on the ground. And we have 2-point masses. That are attached by an inextensible rod that's massless. And these are, let's call them mass M1 and mass M2. And on mass M2, there is a force which we'll call F. And that force holds the system in equilibrium. So there is no friction between the walls and the ground and the mass. And so this is very much like a ladder. And you apply a force F at the base that's horizontal. And the question is, what's the magnitude of F to have static equilibrium? So of course, if you were going to use Newton's laws, you would probably need to do the sum of the forces as well as the sum of the torques. You'd have to identify all the forces on each of the masses. So on mass M1, there's going to be a gravity downwards. Let me draw it. Let's call that M1G. Then there's also going to be reaction forces from the wall. There's going to be a force from the rod on M1, right? Then there's going to be a force from the rod on M2. There's going to be the weight of M2, and there's going to be the normal force from M2. So it's quite a lot of forces and torques to consider. If you were going to do it sort of first-year physics kind of way. But we want to use our new formalism, which is easier, but conceptually takes a little bit more practice. So our first step is to identify the total number of degrees of freedom. So we have two masses that we're describing, and so you know, if it's a three-dimensional space, then there's 6 possible degrees of freedom. So before we can talk about what those degrees of freedom are, you really need to have a coordinate system. So let me introduce a coordinate system. Okay, so now we know that we can use, say, x1, y1, and z1 for mass m1, and x1, x2, y2, z2 for mass m2. So in principle, there are 6 possible degrees of freedom. but this system looks constrained, so let's see how many constraints we can write down. So first of all, let's restrict the problem to the plane. So I can think of two constraint equations for that. Z1 equals 0 and Z2 equals 0. Now, mass M1 is constrained to slide along the y-axis. So we also have that the x position of mass M1 will always be equal to 0. Similarly, for mass M2, the y position will always be 0, since it's constrained to slide along the x-axis, so we can say that y2 is equal to 0. And then we have one last constraint, and that's the fact that the two masses are connected by a rod, so the distance between them is fixed. So if we say that our rod has a length of L, then we can write the final constraint equation as the distance between the two masses. So that'll be x2 squared plus y1 squared equals L squared. So that's 5 constraints. So there's only really one degree of freedom. So let's choose a degree of freedom. And let me choose the angle theta. So we really need to be able to describe the system in terms of our angle theta. So we need to write the positions of the mass, x1, y1, z1, x2, y2, z2, in terms of theta. Now for mass m1, z1 is always 0, and x1 is always 0, so we only really need to write down y1. So the y1 position in terms of theta is going to be L sine theta. And for the mass M2, we only care about x, and so the x position of mass M2 will be L cos theta. So what we really need, though, are the position vectors of where the forces that do no virtual work are applied. Need position vectors of forces that do virtual work. So I've drawn the only two forces that can do virtual work, which are the weight of M1 and the force that's applied on M2. If we were to draw all the forces, you would see that M1, like I mentioned earlier, you're going to have these reaction forces from the wall, as well as the tension force from the rod. But those are forces that can do no virtual work, right? The reaction forces, to do any work, need to have a component that's parallel to the wall, but there's no friction against the wall. And the weight of M2 can't do any force because it's perpendicular to the surface. It can't do any work because it's perpendicular to the surface of the x-axis. Okay, so the forces drawn in blue are the only two forces that can do virtual work. So let me draw our position vectors of where those two forces are applied. It's going to get a bit busy. Let's try green. So the R1 vector is where mg is applied, and then the R2 vector is where F is applied. That's not very obvious, R2 here. So I need to write down R1 and R2 in terms of our generalized coordinate. So the R1 vector, it's only in the y coordinate, and in fact it's just the y position of mass m1. So the R1 vector is L sine theta y hat. And then the R2 vector is in the plus x direction, and it's L cos theta. X hat. Right, R1 doesn't have an x hat component, and R2 doesn't have a y hat component. So what we need now, we need the virtual displacements of those vectors. So we need the delta Ri vectors in terms of delta of our generalized coordinate. In this case, delta theta. So delta R1, I take the variation of R1 with respect to theta. So I apply the chain rule, so L is a constant, and the derivative of sine theta is cos theta, so I'm left with L cos theta delta theta y hat. And the same with delta R2. Delta R2, the derivative of cos will be minus sine, so I'm going to have a minus L sine theta delta theta x hat. So if I draw these on the diagram here, so delta R1 is in the positive y hat direction. And delta R2 is in the negative x hat direction. And they don't have the same length, right? And so you can see that this sort of makes sense, right? The delta R1 and the delta R2 are in, say, a kinematic harmony, right? It's correct that if I move mass M1 upwards, so delta R1 is positive y hat as in the diagram, then to satisfy the constraint, we have to move M2 to the left, and so that's why its delta R2 points to the left. So these delta R's are constrained to each other, right? You can't just have delta R1 point independently from delta R2. And so by doing this formally, you can see how that they're constrained with each other. And you can also think of them a little bit in terms of differentials. How does R1 vary as you increase theta? So delta R1 is written in terms of a delta theta. So when theta increases, so let's say we have a delta theta that's sort of a positive increase in the angle, then delta R1 goes up and delta R2 goes to the left. Okay, so that's what we calculated. We calculated how R1 and R2 vary when we change theta. So we have almost everything that we need here. Let's just be complete and write out our forces. So let me say F1, the force on mass 1. So that's the gravity, and that's pointing in the minus y hat direction. Right? So our F1 vector would be minus m1g y hat, and our F2 vector would be minus f x hat. So the total virtual work is the work of F1 dot delta R1. So we have minus M1 G L cos theta delta theta. And then we have delta R2 dotted with F2. The minus signs cancel. So that's plus FL sine theta delta theta. And for static equilibrium, this must be equal to 0. So if it's equal to 0, then the delta thetas cancel. And we can write, we can write that F is going to be, the L's cancel as well, actually. Right? The delta thetas and the L's cancel. And so F will be equal to M1G, then it's cosine over sine, which is cotangent. And so we did it really slowly, but I mean, this can be done very quickly once you have the hang of it. So for completeness, let's do the other method now where you find the components of the generalized force instead of setting the virtual work equal to 0. So remember, the definition of the generalized force, Qj, is defined as the sum from I equals 1 to capital N of the applied forces dotted with di Ri vector by di Qj. So we've already written the Fi's, but we need the di Ri's by di Qj. And so remember, in this case, Qj, our generalized coordinate, there's only one of them, and it's theta. So there's only one component of the generalized force because there's only one generalized component, and that's theta. So what we need is di R1 by di theta. So di R1 vector by di theta. If I look at my R1 vector that I have here, it's L sine theta y hat. So d by d theta of that is going to be L cos theta y hat. Similarly, for di R2 by di theta, our R2 vector was L cos theta, so d by d theta of that is minus L sine theta. X hat. So if I write down our forces again, F1 was minus M1G y hat, and F2 was minus F x hat. So now we have everything we need to write out the generalized force. So that's F1 dotted with di R1 by di Q by di theta, sorry, plus F2 vector dotted with di R2 vector by di theta. So F1 we wrote as minus M1G dotted with L cos theta, so we have minus M1G L cos theta. And then F2, the minus signs cancels, plus F L sine theta. So think a little bit about what this, so this generalized force here must equal to 0. And of course, almost the same equation, right, as we had before, except there's no delta thetas. But again, the L's will cancel and you'll get F equals mg cos theta. But if we think about Qj again, what is it? So it's mgl cos theta and fl sine theta. And so that turns out that that's the two torques about the origin of the forces M1G and F. Of course, if you solve this the old way, first year of mechanics, you probably would have ended up using torques. Because you would have found that that's a lot easier than using the sum of the forces because you have all these reaction forces. Okay, so there's a very general method. It's equivalent to saying the sum of the forces is 0, but it's general enough that it handles torques and forces almost on the same footing. And it introduces this new concept of generalized force, and it sort of all makes sense that maybe there's a more general concept to say something is not moving, rather than saying separately the sum of the forces and the sum of the forces is going to 0. Okay, so any questions about that? The next example, 3.5, I encourage you to look at it, but we'll go over it on Thursday. Today's lecture, well, I guess the significant amount part depend on an example, but I wanted to cover more theory today. Okay, so if there's no more questions about this problem, let's start a new page, and let's introduce D'Alembert's principle. D'Alembert's principle, in essence, is one of three equivalent ways that we're going to find for doing this new framework of classical mechanics. The three frameworks will be D'Alembert's principle, the Lagrangian method, and Hamilton's method. But they're all mathematically equivalent. They just have, and they're in fact equivalent to Newton's second law, but they have slightly different ways of writing it out. But they're all very, very similar to each other. Okay. So far we've used the principle of virtual work to handle statics, right? What we want to do now is we want to extend this method to dynamics. And that's what D'Alembert's principle is. So recall Newton's second law. So Newton's second law, if we write it as a vector equation, it's the familiar F equals ma. So D'Alembert's principle it's true genius. D'Alembert's principle is that F minus ma equals 0. And that was a truly genius step. And so it looks pretty trivial, right? I'll just move the ma to the other side of the equation. But so why is this such a genius? So D'Alembert's principle, we rewrite Newton's second law with F minus ma equals 0, and we introduce what we call the inertial force. I'm having trouble spelling today. The inertial force. So we introduce this inertial force, which we'll call capital I vector. So that when we write Newton's second law, we have F plus I equals 0. And so yes, we have only just rearranged Newton's second law, and it still doesn't sound like that genius of an idea. So if we treat I just like any other force, then we can apply the techniques of virtual work. So if we consider I as just another force, then the sum of the forces is equal to 0. Then it's just like saying Newton's law, but for static equilibrium. So if we hide the fact that there's an acceleration instead of I, inside of I, and we consider I just as a force, then we've effectively just written Newton's second law as saying the sum of the forces are equal to 0, as long as you consider this inertial force. Or another way to say it would be there must be a frame of reference, for sure instantaneously, where the system appears to be at rest. And that frame of reference might be a weird frame of reference that's presumably accelerated, as the sum of the forces isn't zero. But in that weird instantaneous accelerated frame of reference, you can set things up so that the sum of the forces is equal to zero. In other words, if you consider I as a force, then the system is at rest. And by that I mean, or the sum of the forces is equal to zero. So we can now use this principle of virtual work, which we applied previously to the system where the sum of the forces is equal to zero. As long as we consider this inertial force, we can apply that to dynamics as well. So all we've really done is just written Newton's second law and consider this MA term as an actual force. So that means the total virtual work so I'm going to write delta W just as like the sum over all forces. So if you want, you can put a sum of delta WI's. So the total virtual work is the sum from I equals 1 to capital N, the number of applied forces, of Fi plus, now it could be an inertial force, capital I sub I, dotted with delta Ri must equal to 0. So remember that I now is this minus MA term, and so it gets confusing. What exactly are we summing over? So let me specify that the sum is over the capital N particles, and Fi is the net force on particle I. So if the particles have more than one force acting on them, then the first step would be to sum all those forces to have a net force I. And then you sum, of course, only the forces that can do virtual work. And you can add in the other ones if you want, but they'll just cancel at the end. So now it makes sense that each of these capital I sub I terms belongs to each particle because they're each going to have a mass mi. Alright, so the capital I term is minus the mass of particle I times the acceleration of particle I. So this total virtual work, let me break this into two sums, and it's sum of two vectors with a dot product, so that can be split up. So the first term will be Fi dotted with delta Ri, and then the second term will be the sum from I equals 1 n of capital I sub I dotted with delta R vector 1. Now the first term here we've already dealt with. That's the total virtual work of the applied forces, and we know that we can write that as the sum now from J equals 1 to lowercase n of a generalized force and a delta Qj. Second term on the other side, on the other hand, it's not so obvious how you write it in terms of delta Qj's. So Qj, recall, is the generalized force. So what we really want to do is we want to write the second term here in terms of delta Qj's as well. So we want the sum from I equals 1 to capital N of capital I sub I dotted with delta Ri in terms of generalized coordinates. i.e. in terms of the delta Qj. And from here on out, it's just a bunch of math until we get that result. And a pretty form for Dalamir's principle. So let's get started. So the whole rest of the lecture is going to be manipulating this term of I sub I dot delta Ri. So we have the sum from I equals 1 to n of capital I sub I dot delta Ri vector. So we want to write that out as, let's explicitly put in the definition of capital I. That's going to be the sum from I equals 1 to n. And capital I, remember, is mi times the acceleration of particle I. And so that's the same as saying Ri vector double dot. Right. So it's mi Ri vector Ri double dot vector. Now delta Ri I'm going to express in terms of the delta Qj. So I can write that as the sum from J equals 1 to n of di Ri vector by di Qj delta Qj. Remember, that's just the chain rule to expand the variation of R, which depends on the Qj, in terms of the delta Qj. Okay? So let's now consider this term in brackets. In fact, we'll consider an identity that has this term in it. Now let me do this on the next page. It's not going to fit here. So consider the following identity. take d by dt of mi times ri with a single dot, and that's dotted with the sum from j equals 1 to n of di ri vector by di qj delta qj. So it's almost the term that we have in square brackets, except it's a single dot on the ri. So we apply the product rule to take our time derivative, right? So there's two terms here that are multiplied on either side of the dot product dot. So let's apply the product rule. So I take the derivative of the first part, so that's going to be mi ri vector double dot dotted with the original sum. And then the second term, so that's plus mi ri vector dot unchanged, and now I take the d by dt on the inside, so then I have sum from j equals 1 to n, and if I take the d by dt of that sum, the d by dt and the di by di qj commute, so I can write this as di by di qj of d by dt of ri dotted with delta qj. And this d by dt of ri dot, of ri, sorry, I can write as ri dot. So the term that I had before in red, right, is this part here. So if I rewrite it, so just moving everything else to the other side, so I have mi ri vector double dot dotted with the sum from j equals 1 to n of di ri by di qj delta qj. That's equal to d by dt of the term that I have there, mi ri dot dotted with the sum from j equals 1 to n of di ri vector by di qj delta qj, and then minus the last term above, which is mi ri vector with a single dot sum of j equals 1 to n of di by di qj ri vector dot delta qj. Okay, now the sum over j equals 1 to n appears in all of the terms, right? So it can always be moved to the front of all of the terms. and the delta Qj can be moved to the back of all of the terms. And so I can write this out as an identity without the summation and the delta Qj sign, and it's still true, right? So I can write this as mi ri vector double dot di ri by di Qj. Where there's a dot product there. The sum over j equals 1 to n, and the delta Qj I can omit. And on the other side, I'll have d by dt of mi ri dot dotted with di ri vector by di Qj. And then the last term minus mi ri dot vector dotted with di ri dot by di Qj. Okay. Check the notes if that's correct. That looks correct to me. So now we're going to manipulate this a little bit more. We need to consider another identity. So consider di ri dot by di Qj dot. So that's not a term that appears above, right? So that's the same as saying di by di Qj dot times d by dt of ri vector. So that's the same as di by di Qj dot times, now remember, ri is a function of the q's, right? So if I do the total derivative of r with respect to t, because applying the chain rule, I get it's the sum from j equals 1 to n of, no, sorry, let's use k instead of j. Because we already have a j outside. So it's the sum from k equals 1 to lowercase n of di ri vector by di qk dot. So that's wrong in the notes. In the notes there's a j instead of a k there. And then plus, at the end of the sum, we have a di ri vector by di t. Right, so all I've done from the one line to the next here is I've expanded d by dt of ri vector. We did that actually in the first lecture, where r depends on multiple functions of time and time itself. We found that when you do d by dt, you get two terms. One is the sum of the partial derivatives with respect to all of the coordinates times the generalized velocities, and then plus a term at the end of di r by di t, in case r depends explicitly on t. So the final step here is now I'm doing di by di qj dot of the sum of k of the thing in parentheses, well, the sum plus di ri by di t. So first of all, the last term, di by di qj dot of di ri by di t. Di ri by di t is not going to have any qj dots in it. right? It's only going to have t's in it, if it has anything. So that term is 0. Di by di qj dot of the last term is 0. So you can think of the qj's, maybe say that the Cartesian coordinates, right? So di by di qj dot, maybe it means di by di x dot. So I have this sum here. The sum is going to be a bunch of things times q dot when k equals 1, q dot when k equals 2. So it's going to be something times x dot plus something times y dot plus something times z dot. So I have di by di x dot on the front of a sum of terms where only one of them has x dot. So the only term that's going to be non-zero when I take the partial derivative of di qj dot of the sum is the term in the sum where j is equal to k. So that is going to be di by di qj dot, and the only term in the sum that's going to matter is the di ri by di qj dot. So that's the term where j, or where k equals j. And so that's an easy derivative to take, right? Di by di qj dot of something times qj dot is equal to something. And so the identity that we found here is that di ri vector dot by di qj dot is equal to di ri by di qj. So it just means you can take the dots off from the other side of the equation. But it's not trivial. Okay? So we want this. Let's make this blue. We want to put it where I circled in blue. So we want to change that term to have di ri dot by di qj dot. So I can write oops. So if I put this into our equation, I can write that mi ri vector double dot dotted with di ri by di qj that's equal to d by dt of mi ri dot, and now it's dotted with the other version, which is going to be di ri dot by di qj dot. And the last term stays the same. Minus mi ri dot dotted with di ri dot by di qj. And circle that in blue. I think that's the term that we changed. Okay? Resize my screen. Alright, so on to the next identity. So we still want to manipulate this expression a little bit. So consider this. Consider di by di qj dot of Ri dotted with Ri. So I just apply, Ri dot dotted with Ri dot vector. So I just apply the product rule, right? So this is a scalar product of two vectors, and I want to do di by di qj dot of that. So I can just apply the product rule. So it's going to be di by di qj dot of Ri dot dotted with Ri dot plus Ri dot dotted with di Ri dot by di qj dot. So that, of course, is just 2 times the same thing. So that's the same as 2 times Ri dot dotted with di Ri dot by di qj. So that allows me to rewrite this as Ri dot, when dotted with di Ri dot by di qj dot, is equal to a half of di by di qj dot of Ri dot dotted with Ri dot. Now, a vector dotted with itself, that's a half di by di qj dot times Ri dot squared. It's the length of Ri dot squared. It's the scalar product of Ri dot with Ri dot. So this term here, oops, this term here, Ri dot dotted with di Ri by di qj dot, that appeared over here. Now similarly, in this whole thing, it didn't matter too much what the variables were called, and so it's trivial to show that Ri dot dotted with di Ri dot by di qj, so qj not qj dot, yeah? It's the exact same math to show that that's equal to a half di by di qj of Ri dot squared. Right, and the derivation that I just did above, it didn't matter that I was differentiating with respect to qj or qj dot, right? We didn't never use the fact that that was a dot or not. So of course, if I just rewrite the whole thing without putting dots on the QJ, you're going to get the same answer without dots on the QJ. Okay. Alright, so I think now we have all of our properties. Now we've got to go and put everything together. So the term we were working on was the last term on this page, right? So we have mi ri double dot dotted with ir by equals the rest. So let me rewrite that down. So we have mi ri double dot dotted with ri by qj. That's equal to d by dt of, we have mi ri dot, but now we have this green thing, right? So I'm going to rewrite the part in green as what we just found. So I have mi, but then the part in green is a half di by qj dot of ri dot squared. And that's minus, and I'll do the same thing with the second term, right? So that's the same as the term in green, except it doesn't have the dot on the qj. So the second term I can write as mi times a half di by qj of ri dot squared. So note there's a dot on the first di qj and not on the second. Now let me just rearrange this a little bit. So that's the same as d by dt. I'm going to move the mi times a half inside of the di by qj dot. I'm going to write that as a half mi ri dot squared minus, and then do the same thing here, and put the di by qj at the front. I'm going to have a half mi ri dot squared. Alright, I can move the half mi inside or outside of the di by qj because half mi is just the front. Now half mi ri squared. So let me just introduce a new variable I'm going to call capital T. So let T, capital T, or Ti, be defined as a half mi ri dot squared. So that Ti appears in both terms, right? They both have a half mi ri squared. So that means that our original thing is d by dt di by qj dot of Ti minus di by qj of Ti. So let's think a little bit about what this Ti is. It's a half times the mass of each particle. Remember, mi is the mass of each particle. And then Ri is the position vector of each particle. Right? Each particle had a net force F applied to it, and the position of the particle was Ri. And so Ri dot, of course, is the speed of the particle. So Ri dot squared is v squared of the particle. So Ti turns out to be the kinetic energy of particle I. And so this is probably one of the most important mathematical steps in this, all of the course, is to do this whole manipulation and find out that you end up with the kinetic energy. So what were we doing in the beginning? Because now we've completely lost track of what we were trying to do. Remember, we'd written down D'Alembert's principle, and there was two terms in it. The first term we'd already handled with the generalized force last time, and then we were working on the second term here. So now we finally got it in the form that we like. So finally, we can write our sum from I equals 1 to capital N of the capital I dotted with delta Ri. That was the whole goal of this mess. Alright, so that's this inertial force dotted with delta Ri. So we found that we could write that as minus the sum from I equals 1 to capital N of Mi Ri dotted with delta Ri. And then we manipulated this term. So that was equal to minus the sum from I equals 1 to capital N of Mi Ri double dot dotted with the sum from j equals 1 to n. So this is part that we did before, right? We're just rewriting out the delta Ri. So that was di R I by di Qj delta Qj. Now, nothing prevents me from putting the two sums together and maybe inverting their order. So let's say I have the sum from j equals 1 to lowercase n, then I wrote the sum from I equals 1 to capital N. And then we saw that we can write this term here as d by dt of di Ti by di Qj dot minus di Ti by di Qj. But maybe I changed my mind. Oops. So that maybe now I want to bring. So here I brought out the sum with the j out in front of the MIRI double dot. But maybe I actually want to bring the sum over I inside of my derivatives. So let me define T to be the sum from I equals 1 to n of Ti. Alright, so if I bring in the sum over I up to uppercase n, it can go right through the derivatives and end up as a sum over the Ti's. And so I'm going to introduce capital T as a sum over Ti's. So that's the sum of the kinetic energies of all the particles. So it's the total kinetic energy of the system. So doing that, we finally have our original thing, which was the sum from I equals 1 to capital N, capital I vector sub I dotted with delta Ri vector. That's equal to minus the sum from j equals 1 to n of d by dt of di t by di Qj dot minus di t by di Qj. So I guess I forgot to put the delta Qj at the end here. I forgot it. it there as well. So let's put this all together now. So the principal virtual work, including now this inertial force, so the total work was the sum I equals 1 to n of the applied forces plus the inertial forces dotted with delta Ri. So that was equal to the sum from j equals 1 to lowercase n. So the Fi we know that we could write in terms of the Qj delta j, but the second term with the capital I is also going to have a delta Qj at the end. So let me write that term in first. That's Qj minus d by dt of di t by di Qj dot minus di t by di Qj. Delta Qj. Now, this must be true for all delta Qj. They are independent. So that means that each term in the sum must equal 0. So each term equals 0. So if I write each term equal to 0, I can write this as d by dt of di t by di Qj dot minus di t by di Qj equals Qj. And that's the useful form of D'Alembert's principle. Now, does this look familiar? And the answer is yes, it should look familiar. So recall from variational calculus the stationary value of the integral L, which could depend on, say, Q1 to Qn, Q1 dot, and T, dt, the stationary value of that subject to K constraint equations was given by the modified Euler-Lagrange equation, so modified to include the Lagrange multipliers. And that gave us that d by dt of di L by di Qj dot minus di L by di Qj was equal to something that we called Qj at the time, but it was a sum from I equals 1 to k, so over the k constraints, of lambda I di Fi by di Qj. The constraint equations were Fi equals 0. So that kind of looks similar, right? You have a d by dt of a di by di Qj dot, and then you have a minus di by di Qj, and then equals something on the right-hand side. So the Qj here for the generalized forces, remember the definition of the generalized force was the sum from I equals 1 to n of the force Fi dotted with di Ri by di Qj. So it appears that this lambda I has something to do with Fi, and the di Ri by di Qj must have something to do with the Fi functions. So let's put that in a sentence. So it appears that D'Alembert's principle is the solution to a problem where one wants to find the stationary value of the kinetic energy it's not really the stationary value of the kinetic energy so much as the stationary value of an integral of the kinetic energy. Which we'll call S to be some integral of the kinetic energy over time, right? Where forces are related to constraints on the coordinates. All right, when you compare what we obtained for D'Alembert's principle, especially if you plug in for the generalized force the definition in terms of the applied forces, mathematically it looks very similar to the problem of finding the stationary value of the integral of some function L, where L would be t, subject to some constraints between the coordinates given by the Fi. And so somehow this generalized force has something to do with the constraints. And So philosophically, what we're saying is that the kinetic energy of the system is going to depend on the forces that are applied on the particles, and that makes sense. And somehow the particles are constrained to move because of these forces. They can't just move in any direction they want. There's some sort of a constraint due to the forces in how the particles can move. And so philosophically, that's what we've done. This is related how the kinetic energy relates to constraints and forces, and positions because of forces. We'll find out in later chapters that the condition for the kinetic energy to be stationary is related to what's called Hamilton's principle. And Hamilton's principle reformulates all of mechanics by saying, this is the condition. The condition is that the kinetic energy be stationary. Now, find the equations of motion based on that. And that is equivalent to Newton's second law. So we've proved it the other way around now. We've started with Newton's second law, and we've essentially arrived to what we'll call later Hamilton's principle. For now, we're just calling it D'Alembert's principle. Okay? That was a lot of math to absorb, and it has a lot of consequences that you should ponder. That's all I was going to do for today. Are there any questions? Okay, if there's no questions, we'll stop here. Thursday we'll work on problems and answer questions for the assignment that's due on Friday. When are you going to have? The last week's videos I should be posting sometime today. It takes a while for them to convert. And it's a manual process, so I can't. It's hard. Okay. Thanks, everyone.